Welcome back. Let's take a look at what we learned about efficiency, conservation, and energy in general before we start in on our challenge. We've seen a direct correlation between the amount of greenhouse gases in our atmosphere and the amount of trapped heat. Some of those greenhouse gases are carbon dioxide, water vapor, and methane. And although they are a small amount of the overall atmosphere, they have a big impact. But it's those carbon-based molecules that we can change the amounts. Carbon is abundant. It's everywhere. We are carbon. It has 4 exterior electrons that allow it to connect in a lot of great ways to create things like hydrocarbons, which are fossil fuels. Burning those fossil fuels brings that carbon out and releases it into the atmosphere. Carbon dioxide, even though it's less than 1% of our atmosphere, is one of the biggest contenders here. Human activities caused a measurable amount of carbon dioxide, especially since we started burning those fossil fuels. Most scientists are in agreement that carbon dioxide levels directly have an impact on our climate. Greenhouse gases get their name from the greenhouse effect. Here you can see sun's radiant energy is reflecting light off the earth. Some of that light makes it through the atmosphere, but then when the heat comes back up from the earth, as the earth releases that heat, it gets trapped. So we have trapped thermal energy in our atmosphere. If we heat up the air, we start to see changes in weather, and if we see long-term changes in weather patterns, we see change in climate. This is all part of a natural cycle called the carbon cycle, which takes carbon in different forms from the lithosphere, hydrosphere, atmosphere, biosphere, and constantly flows it. The lithosphere is the ground, it's the rocks, it's the minerals, it's the fossil fuels below us. We started increasing this flow of carbon in different forms from the lithosphere as we started to burn it during the Industrial Revolution. To help lower our carbon footprint, we can use energy more efficiently or choose to conserve that energy. Efficiency is all about using the most energy out of the system. We put energy in, but some of it's dissipated as thermal energy. This is why a bouncy ball doesn't bounce all the way back up. Most transformations in general are not very efficient, but technological innovations use that electricity more efficiently. Essentially, efficiency is doing more with less. Efficiency puts technology in charge. Conservation puts us in charge. These are the behavioral choices, how we choose to use less energy, turning off a light switch, wearing a sweater instead of cranking the heat. These two together help us save energy. Efficiency from the design point of view and conservation from the use. We're going to start looking at the design point of view, efficiency, as we look at our home challenge. Electricity is one of the biggest energy uses in the home. And plug loads are devices that use electricity. These are devices that bring us comfort, entertainment, safety. However, managing their use can reduce electricity consumption. You can look at that a couple of different ways. We can buy more efficient technology, more efficient devices that use energy better. Or we can choose to turn these devices on and off. Phantom loads are a great example of conservation. These are devices that use electricity even when they're turned off. These are devices like digital clocks, timers, remotes, wall cubes, computers. Anything that has memory built into it is often using electricity even when you aren't using it. Phantom loads may not go into the design of an efficient home, but they're part of the conservation choices you could make once the home's designed. When you're designing a home, you can think efficiently about how thermal energy is transferred. Buildings are designed to separate the inside and outside air. This is what we call the building envelope. This envelope includes all the outer surfaces, walls, floors, doors, roofs, and windows. Anything that contains this energy system. You're pumping in heat through burning natural gas or a geothermal system or electric infrared heat. And then you want to keep it inside. It's kind of like taking a thermos and keeping it insulated. When designing an energy efficient home, you should be thinking about comfort and health over the energy efficiency. Even though it's really great to say you saved a lot of money, you want to make sure it's comfortable. If you make it uncomfortable, you're going to make less conservative choices to reduce energy in the future. We can build up this envelope by insulating the outside. So insulating those walls, those floors, those doors, everything, preventing that thermal energy from going in or out of the building. And a lot of this thermal energy is transferred through air because air holds moisture. Moisture holds thermal energy. It holds heat. So that resistivity, that R value, the resistivity that insulation has to that transfer of heat, higher R level, more resistance. Lower R level, less resistant. So you want an insulator that resists thermal energy transformation. The walls are important, but they're pretty much solid. Doors are always opening and closing. Simple way to fix that is just close your doors. However, weather stripping is a great way to add that R value, that resistivity, that resistance to thermal exchange. Doors shift over time. Just like a house settles, your cardboard house may be settling as well when you're designing it. So keep that in mind. Make sure the structures are strong. If you have multiple doors, like a vestibule or a storm door, some doors have a solid door and a glass door that you can open and see through. This prevents large amounts of air, whether it's a full vestibule or just a storm door. It keeps large amounts of air from entering at once. A lot of insulation is about creating air gaps. Air gaps create a break from the inside and the outside. A vestibule or a storm door, so a break in doors, creates a break between the inside and outside of that envelope. Windows not only open and close, but they're thin. They're just glass in most cases. So the materials really make a big impact. There's different types of glass material, especially when it comes to the frames. A lot of schools and older buildings use metal, which is a conductor. It allows that thermal energy straight through. Vinyl, wood, composite, cardboard even, these are insulators. They don't let a lot of thermal energy through. So when you're building a frame for a window, you'd want it to be out of something that is an insulator. Or low E glass, which is hard to scale, but it's a specific material that reflects light, extra light, off of the window. If you let less radiant energy through, then you're letting less thermal energy through. But you're still letting people be able to see that visible light, see out and enjoy the beautiful view. Panes of glass create air gaps, just like multiple doors create big gaps of air for insulation. The more panes, the better, because you have more air gaps in between to insulate. You can't stick a bunch of insulation in between windows and still be able to see through it, but those air gaps work the same way insulation would. It creates pockets of air. A single pane allows that thermal energy straight through. Double pane, now you have a gap of air. Triple pane, now you have 2 gaps of air. So it's double insulated. And since windows are usually originally in the design process big holes in your house, you need to make sure all the gaps around the edges of that window are insulated. So just like in a real house, start thinking about that for your smaller model house. Another way that you can conserve energy is buying efficient technology. We can look at this energy guide to find out whether these different devices, these different appliances are energy efficient. If you were shopping around for different devices, you might want to know the key features. You might want to know the make and model to compare different devices of the same design. You can look at what it costs for 1 year estimated to run that device. This amount of money is directly related to the amount of energy. You can also compare it to other devices and see that other devices in this range are much more expensive to run for a whole year. So that means they are much less efficient. They're using that energy less efficiently, less effectively. It also gives you an estimated annual electricity consumption, which, if we know the amount of kilowatt hours and we know the average cost per kilowatt hour is about 13 cents, that $48 and that $3.96 are connected. Energy Star appliances are always going to be guaranteed by the government to be the most energy efficient. So if you're shopping around for energy efficient appliances, always look for Energy Star. Geothermal is exactly what it sounds like. Geo, earth, thermal, heat. It's heat from the earth. As the core radioactively decays and the amount of pressure from all the rock on top, it creates a lot of heat below. This keeps the earth, or the mantle below us, relatively the same temperature. We can use that heat, that naturally existing heat energy, to heat homes, grow crops, and even generate electricity if we can generate enough steam. Here's an image of a geothermal power plant. On the right, we have a couple examples of homes that are heated using geothermal energy. These homes use the natural heat underneath the earth instead of burning natural gas. Let's take a little field trip to energy manager and expert Jim Brown's house. His home is heated using geothermal energy, but then he contains that energy using very specific tactics. See if you can pick them up.
So our house is heated with a geothermal system, which takes the constant temperature of the earth as a starting point, roughly about 55 degrees, to heat or cool our home. It also has what's called a desuperheater, which takes the leftover heat after that to preheat our hot water. And so that goes to a preheat tank here, and the preheat tank then goes into our electric hot water heater. The rated guide on the electric hot water heater is $573 a year for a total of 4,773 kilowatts per year. So far in 4 years, we've yet to reach that 4,773 kilowatts, so it kind of shows you the effectiveness of the system. It is a forced hot air system, and our house is sealed very well. Typical homes, Energy Star homes, are rated for 3 air changes per hour at 50 pascals. Our home is under 1 air change per hour at 50 pascals. Because of that, we have a heat recovery ventilator. So all the fans in our bathrooms, the air that is pulled out of the bathrooms goes through this, and the air streams don't actually interact with each other, or they don't mix. The air doesn't mix, but they pass over each other, and 70% of the heat is recovered in incoming air to the house. So that's anytime air is brought into the house, it's heated from the outgoing air. Our windows have low E glass, which minimizes the amount of ultraviolet and infrared light that comes in through the windows, and it doesn't affect the amount of light that comes in. For the unfinished portions of our basement, we have what's called blanket insulation. It's a cheap and effective way. But then for the areas between our floor joists, we have spray foam insulation, which is much better at sealing and insulating, has a high insulation density.